This lesson will continue to explore aspects of spectroscopy. I mentioned before that spectroscopy has four different pieces of information that it tells us. The first is it tells us how many different types of that particular atom that we have in the compound. For proton NMR spectroscopy, it tells us how many different types of hydrogens. And for C-13 NMR spectroscopy, it tells us how many different types of carbons there are. The second thing it tells us is the shift value gives us an indication as to the electronic environment of those particular atoms. For C-13 NMR spectroscopy, that's typically all we ask for. But you can actually generate a C-13 NMR spectroscopy spectrum that produces what's called splitting. So this particular compound right here, 1-bromo-2,3,3-trimethylbutane, has 5 different types of carbons. Carbon labeled A, B, C, D, and E. Notice how all 3 of these methyl groups right here are labeled E, and when we look at the spectral data, those 3 carbons are producing a similar, what's called a peak cluster. So this peak cluster over here labeled E is due to these 3 methyl groups. Why do the 3 carbons labeled E produce the same peak cluster? And the answer is they are chemically equivalent. And you can actually use the same chlorine replacement tests, only instead of taking off the hydrogen and putting a chlorine on there and then naming it, you just take off the whole methyl group and put a chlorine on there and generate a name for your compound, and you would get the same name regardless of which of these 3 methyl groups you pulled off. So that's how we can tell that they're chemically equivalent, but we can also just tell because they're all producing the same peak cluster. Now, so that's the idea of how many different types of carbons there are. The approximate shift values right here should make some sense to you as well. If you see peaks that are above 50, then that means that the carbon that is responsible for those peaks is associated with a highly electronegative atom. Bromine is a highly electronegative atom, so the carbon directly connected to the bromine is going to show up with the highest shift value. Those atoms that are furthest away from the bromine, the carbons that have the most electron density, because they're over here just grazing contentedly on their electron density associated with the hydrogens, are going to be more shielded and have a lower shift value, still relative to TMS. So we still use TMS as the solvent in C-13 NMR spectroscopy. Peak multiplicity refers to the number of peaks in a cluster. So in this C-13 NMR diagram right here, carbon A has 3 peaklets in the cluster, and so we can go ahead and assign it a peak multiplicity of 3, meaning that there are 3 kind of sub-peaks that collectively comprise this entire cluster. And if you look at carbon A, there are 2 hydrogens attached to it. We're going to use that same criteria to look at carbon B, C, D, and E. The peak multiplicity for B is 2 because if you look at the peak labeled B, there are 2 peaks. So this is a 2. For carbon letter C, it's a 1. Peak multiplicity is 1 because it just makes 1 peak. D is 4 and E is also 4. So peak multiplicity is a numerical statement that tells us how many individual peaklets are found in that peak cluster. Now, if we look at the structure of this, carbon B has 1 hydrogen, carbon C has 0 hydrogens, 1 and then 0. Carbon D and E's all have 3 hydrogens. So there's 3 for carbon D and 3 for carbon E. Based on the results of your table, what is the relationship between peak multiplicity and the number of hydrogens attached to the carbon? And we can express this as a mathematical formula that peak multiplicity is equal to hydrogens plus 1. So if you have 2 hydrogens, we expect the peak multiplicity to be 3, 1 hydrogen, it's 2, etc. If we say that backwards now, that means that if your peak multiplicity is 3, then the number of hydrogens is going to be 1 less than that. Or a triplet tells us that this carbon has 2 hydrogens. The doublet tells us that that carbon has 1 hydrogen. The singlet tells us that that carbon has 0 hydrogens. And these quartets tell us that their associated carbons have 3 hydrogens. Peak multiplicity is a result of peak splitting. So what happens in carbon-13 NMR is that their peak was split because of the attached hydrogen. So imagine that carbon A, which is right here with these two hydrogens, if the hydrogens weren't there, then the peak would be this dashed line. That's what the singlet would look like if carbon A had never went and had hydrogens. It was a bachelor. But because it has these two hydrogens, each of the hydrogens produces essentially a valley. If a carbon only has one hydrogen, then that one hydrogen will produce a valley and it cuts that peak into two pieces. So this is the rationale, that a peak on a carbon that has three hydrogens gets cut 3 times and ends up making 4 new peaks. So peak clusters are classified by the number of peaks in the cluster. I've already used these terms: singlets, doublets, triplets, quartets, etc. Identify each of the clusters as singlets, doublets, triplets, or quartets. So A has a peak multiplicity of 3, and then B is 2, and C is 1. So 3 is a triplet. B is, there were 2 in B, that's a doublet. C was a singlet, and then D and E both had 4, so that's referred to as a quartet. And we often, as chemists, just abbreviate these with, for the sake of simplicity, we'll refer to it as a peak that's a T, a D, an S, and a Q. So you'll see these actually written next to the peaks. It's to help people identify how many individual peaks there are in the cluster. In case the particular NMR instrument doesn't produce very clear data, they'll go ahead and label it for you. They'll put a little Q up above it, or over here an S up above it. So question number 5 asks me to look at this spectrum right here and assign each of these peak clusters to one of the 4 carbons in 2-bromobutane. It again is helpful for us to know how many hydrogens are on each of these. So if I go ahead and label these, this carbon right here has 1 hydrogen. 1 hydrogen will split the peak once. So we expect for this doublet right here, the only doublet anywhere in my spectrum, to correspond to this hydrogen right there. So that's my doublet. It also makes sense that this carbon right here has the highest shift value because it's directly underneath the bromine. Letter B is a triplet, which means that it comes from a carbon with 2 hydrogens. This is the only 2 hydrogen carbon anywhere in the compound. So with some confidence, I can assign that a letter B. It's also the next highest peak in the spectrum because it's 1 step away from a bromine to a methylene carbon. Letter C right here would be 1 step away from the carbon that's connected to the bromine, but it's the methyl group. So this would be C. And then out here on the end, this is carbon letter D. It has 3 hydrogens, so we expect it to be a quartet. And it's kind of isolated from the whole mess of the bromine. It's several steps away. And so notice how that effect kind of dampens as a function of time. Let's see if I can get these on. Well, I'll do this without you. Okay, so here we have the original spectrum. I just took it and went ahead and attached letter labels. So you can call these any letters you want, but as long as these letters match up with the corresponding letters in your 2-bromobutane, then you've demonstrated that you understand the question, which is your goal. All right, the problem with all of this is that carbon-13 NMR spectra is based on carbon-13. And carbon-13 only makes up about 1% of all of the carbon in a typical organic compound. The most common isotope is carbon-12. The problem with carbon-12 is that its nucleus doesn't actually have a net magnetic dipole. So it's NMR insensitive. Carbon-12 doesn't respond in a meaningful way to NMR spectroscopy, but the carbon-13 does. But the problem is that since only 1% of your compound is carbon-13, you are essentially conducting an experiment on a very diluted sample. It's always going to be 1% of what you think the concentration is. And this creates a problem because every time you run any type of experiment, there's going to be some background noise. It's based on random fluctuation of radio waves in the universe, slight impurities in your compound. And if you start taking these peaks for a carbon-13 NMR and then splitting them, it actually makes them shorter and shorter and shorter, and they start to hide out in the noise. Also, if you have a carbon-containing compound with lots of carbons, which is really common in an organic chemical experiment, then these peak clusters actually start to overlap with each other. So I chose some examples where there's a lot of space between D and C and B and A, so you can see them all clearly. But imagine that this was a different molecule and C and D were sitting directly on top of each other. And so imagine that you're holding up your hand so that it throws a shadow on the wall, and then you hold your other hand a foot away from your first hand, and you actually should be able to see both shadows simultaneously. But if you now take your hands and set them on top of each other, the shadow loses the detail of the individual fingers, and you can't really tell what's going on anymore. And so what they decided to do, what's most common in carbon-13 NMR, is they disconnect, they decouple the hydrogens from the carbons. And so this right here is the spectrum of a coupled 2-bromobutane. And notice how each of the carbons is split a certain number of times based on the hydrogens that are connected to that carbon. And this is really nice, useful information, but it's just really hard to collect. And so for experimental ease, it's more common that you'll see what's called a decoupled C-13 NMR spectrum, where instead you just don't get any peak splitting at all. There's no multiplicity, everything's a singlet, and it does not matter how many hydrogens are connected to each carbon. So what structural information is lost when we move from this spectrum to this spectrum right here, the decoupled spectrum, is we no longer know how many hydrogens are connected to each carbon. And that's essentially the cost of collecting real data. In a laboratory, trying to run a coupled C-13 NMR spectrum is just a mess. And so when we think about what information do we realistically get out of C-13 NMR, we pretty much only get the number of different types of carbons. There's 4, because I see 4 peaks, and we know their approximate shift values, but we don't actually know what the coupling is. We don't know how many hydrogens are associated with each of those carbons. So what basic structural information does a decoupled C-13 NMR still tell us? Well, and this is these is important enough to me that I'm going to number it. First, it tells us the number of chemically unique carbons, and 2 is it tells us the shift values, and or in other words, an approximation of the chemical environment of the carbons. Okay, so that's why it's still worth doing C-13 NMR. It's the most common way you see it is decoupled, and chemists just realize that we're losing a little bit of data, but we're still getting a lot. It's definitely worth conducting a C-13 NMR experiment. In C-13 NMR, does the height of the peak tell you exactly how many equivalent carbons are represented by that peak? And the short answer is no, and the long answer is no. So when you are looking at a C-13 NMR, don't try to read into how tall these peaks are. Each of these peaks represents 1 carbon, but they're all different sizes. And so this is common with C-13 NMR. There's no connection between the height of the peak or the area underneath the peak and the number of individual carbons. That is different than what we see in proton NMR spectroscopy, where the area underneath the peak or the integration absolutely is useful information in proton NMR. And we can get away with that in proton NMR because proton NMR is like 99% of the protons are, 99% of hydrogens are protons. And so we're not diluting our sample by choosing an isotope that is less abundant like we do with C-13 NMR spectroscopy. Okay, so here is the dreaded memorization list, and it's actually really helpful. If you have a carbon that is part of an alkyl group, the shift values will typically be between 0 and 35 for a methyl group, 15 to 40 for methylene, and 25 to 50 for methine. If it's a quaternary carbon, it's between 30 and 40, etc., etc., etc. So we're going to go ahead and look at examples that show us how to apply this table, but this is a table that you should become very familiar with. So using the information in the table above, draw a coupled and decoupled C-13 NMR spectrum of 3-methyl-1-pentene. So I'm going to go ahead and pull up ChemDraw, clear my plate, and I have 3-methyl-1-pentene. So I need 5 carbons. The alkene is occurring at the 1 position, and there is a methyl at the 3 position. I'm going to try to approximate what the C-13 NMR diagram for this compound will look like. So on the baseline of a typical C-13 NMR, we have ppm, and over here will be my 0 point. Oops, that's a 0. And then let's take a look at the table. Notice how I have pretty much simple alkanes, and then I have an alkene. Looking at the table, alkenes generally show up between about 100 and 150. So that means that let's go ahead and set 150 at the high end of this. And I'm going to do the decoupled spectrum first because that will be easier. So I'm going to use this as a decoupled is the one where each carbon produces a single line. So let's go ahead and decide how many carbons this compound, how many peaks it would produce at a C-13 NMR spectrum. Well, this alkene is different. So this would be 1 peak. These 2 alkene carbons are different. Here's the only methine anywhere in the compound. This is the only methylene anywhere in the compound. And these 2 methyl carbons are different from each other because one is closer to the alkene and one is further away. So that means that I actually have 6 different lines that I need to put somewhere in the compound. So I'm going to kind of preload those 6 lines and get them ready, and then I'll have to decide where in the compound to place them. Okay, so where would they go? Well, peaks 5 and 6 are methyl groups, and methyl groups generally show up right below 20. Sometimes they can creep up above 20, and they're going to be relatively close to each other. So I'm going to put them down here on this end, fairly close to each other. Those are my 2 methyl groups. My methylene carbon is going to be a little bit higher, but not that much higher, so I'll put it there. My methine carbon is going to show up a little higher still. And then we have the 2 alkene carbons. This alkene has 2 hydrogens, which will mean that it gets to pull more electron density from each individual hydrogen. And so it ends up being more shielded. This carbon right here only has 1 hydrogen, so it's going to be a slightly higher shift value. So this is something of what the decoupled spectrum would look like right here. And I can check this by cheating. And so I can go ahead and generate a C-13 NMR spectrum of my compound. And then I'll just copy this and bring it back, and we'll see how I did. Let's see, kind of want the same scale on this one, so it goes from 0 to about 150. We'll try to set the numerical values the same, and I was okay. Like, not the greatest, but I didn't even have a very precise scale, so I feel pretty good about this one. So the idea was that we went ahead and took these different carbons and we spread them out across the spectrum. Now, as for the coupled spectrum, so this is a decoupled spectrum where everything is a single line. The coupled spectrum is going to be a mess. Notice that the peak here at 11.7, it is a methyl group, so that means there are 3 hydrogens on it. So it would need to be a quartet. And so we would need to come up with a way of drawing 4 of these lines in here, which would then be difficult to distinguish between the 4 lines that we'd see for the peak at 20. The peak at 29.5 would be 3 lines. 39.7 has 1 hydrogen, so it would be a doublet. So rather than show all those individual lines, let's just use those 1-letter abbreviations. This is going to be a quartet that we'd see right here. The peak at 20 represents a methyl group. A methyl group has 3 hydrogens. If you cut something 3 times, you have 4 pieces, so that's also a quartet. At 29.5, that would have 2 hydrogens, so a triplet is what we'd expect. This would be a doublet. This peak at 109.5 right there has 2 hydrogens on it, so that would be a triplet. And then 146.1 has 1 hydrogen, so that would be a doublet as well. So we can kind of cheat on this one and show the coupled spectrum as just these letters right here. When I said 109.5, it struck me that that's an oddly familiar number, but that's the bond angle of a tetrahedral compound, which is a familiar number to us, but totally unrelated. Okay, so now we've kind of walked through the basics of what we learn from C-13 NMR spectroscopy, that we're using a lot of the same rules that we saw with proton NMR spectroscopy to think about shielding and de-shielding, but really all we're focusing on is the number of different types of carbons in the compound and the shift values that are approximately associated with those carbons because of their surrounding environment, their functionality. That's pretty much it for new material for this particular lesson. Now the key part is to go ahead and answer the 3 practice problems. I'm going to walk through one of them right now, and the other 2 are assigned to you as homework. There's no textbook problems associated with this lesson, so we just need to wrap up these 3 problems. These 3 problems are all similar in that I'm giving you a mass spec, I'm giving you the IR, and I'm giving you a C-13 NMR. And from those 3 types of spectroscopy, you need to build the compound. So I've kind of walked you through the first one with quite a bit of discussion. So let's go in order that I typically approach these, and the first thing that I'll look at is the mass spec. So here's the mass spec for the compound. Let's see, problem number 1, the best place to start is looking at the mass spectrum. This molecular ion is really hard to see, and that's why I was looking for a label, and that's why I went back up and read it. Sometimes they'll conduct a completely separate experiment. If I were to run this in a laboratory and this is the spectrum that I generated, I might think that the compound had a molar mass of 73. But there's this little blip way up here that seems odd to me. So if I encounter that, I would wonder in the laboratory whether or not the compound had a mass, the molecular ion was at 73 or 88. Now, an odd numbered molar mass is actually kind of rare. It usually means there's a nitrogen in the compound, and we don't actually see a lot of those. So one of the things you can do to check when you have, is this just noise or some kind of weird blip in my instrument, is you can do what's called a soft ionization technique. And normally when you run mass spec, you blast that thing with a high energy electron and it causes the entire molecule to shatter. If instead you just kind of nudge it with an electron, you'll still make the molecular ion, but it won't shatter, and your mass spectrum will produce only a single peak that represents your molecular ion. So when you ask, well, how does anybody know what the molecular ion is just looking at the spectrum? The answer is they conducted a second experiment that they didn't show you the data for, but they did tell you the result of that experiment was that I know my molecular ion has a mass of 88. Okay, so because I know the compound has a mass of 88, it is an even numbered value. An even numbered value would suggest that it's probably not a nitrogen. Nitrogen gives your molar mass an odd numbered value, or at least an odd numbered nitrogen, odd number of nitrogens. And I'm going to hope that I didn't come up with an example where I gave you multiple nitrogens. Okay? There doesn't appear to be any M+2 peaks in here. So bromine and chlorine have obvious M+2 peaks. I'm barely even seeing the M peak, not seeing any M+2 peaks. So it doesn't seem like there's a bromine or a chlorine in the compound. There's also nothing going on in the high 70s and the mid 60s and the low 50s. I do have some stuff going on in the low 70s and the mid 50s, but when you see these 3 together, that suggests the benzene ring. Let's just take a brief look at problems 2 and 3. So here I see something in the high 70s, nothing in the mid 60s, nothing in the low 50s. This compound doesn't look like it's a benzene ring either. There's my nice looking benzene ring. High 70s, mid 60s, low 50s. So problem 3 has that characteristic telltale sign of a benzene ring. High 70s, mid 60s, low 50s. You also have a 4-fingered region, sp2 carbon, hydrogens, carbon. I'm doing this problem for you. I'll let you look at that now. But in this compound right here, I don't see any evidence in the mass spec of a benzene ring. So now I have to deal with the fact that there are 88 units of mass. Well, that could be 7 total carbons, and because 7 times 12 gives me 84, but that only leaves me with 4 hydrogens to work with. So if there were 7 carbons, then I would use up all of my mass coming up with a molecular formula of C7H4. That's weird. Normally you see about twice as many hydrogens as you have carbons. Something like C7 would generally give you 14 hydrogens instead of 4. So the compound probably has fewer than 7 carbons. And let's just say 6. I'm going to see if there's other non-carbon atoms Of the honk X atoms, I've kind of ruled out the nitrogen. There doesn't seem to be any good evidence of halogens right there. So the only remaining atom that I might have here that's not a hydrocarbon might be oxygen. And I can check for that in the IR. So here the IR, I'm looking to see if there's anything that jumps out at me. And it does. This peak at 3400 is screaming alcohol. And that's actually one of the most obvious peaks that you see in an IR spectrum. And so I don't see any peaks right here just above 3000. So that would suggest, and there's nothing going on at 1600. There's kind of this little whoop right there, but I don't know. Usually if it's a carbon-carbon double bond, it'll go down at least halfway. So what it suggests to me is I have an alcohol, there's no double bonds. There is this very large peak at 1150, but that's usually because there's carbon-oxygen bonding. And if you have an alcohol here, you're also going to see something in that 1000 to 1200 box. So from the mass spec and the IR, I have less than 7 carbons, 6 carbons or fewer. I have an alcohol somewhere in the compound. That's all I've gotten so far. Now let's take a look at the carbon-13 NMR. There are 1, 2, 3, 4, 5 different peaks. That's the one thing that carbon-13 NMR should tell you, the number of carbons of unique types of carbons in the compound. I also have this peak at 70, which is really high. These peaks at 40 and lower would typically suggest it's just a typical alkane. But a peak at 70, let's go back to our memorization list, right there. Okay? 65 to 90 is a carbon-carbon triple bond. No. 50 to 65 is usually an alcohol or an ether. And it can go a little higher, so let's modify that and call it 70. So that right there is the carbon bound to the oxygen is showing up in my C-13 NMR. So there I have an alcohol, and then there's 4 other carbons. Now we're ready to start building this thing. Based on my C-13 NMR, there are at least 5 carbons. 5 times 12 is 60. Because the IR is screaming alcohol at me, there's also an oxygen. 60 plus 16 is 76. If you remember, my molecular ion peak was at 88, so that leaves 88 minus the 76 that I've already accounted for, gives me 12 units of mass. So let's call them 12 hydrogens. This gives me a molecular formula of C5H12O. And this is just an alcohol with 5 carbons and really nothing else. So the simplest Occam's razor tells you to start with the simplest assumption. I've got a straight chain carbon with an alcohol at either the 1, 2, or 3 position. Let's try that one. Well, if it's 1 pentanol, let me go ahead and start drawing those. So what I'm suggesting is that based on what I've gotten so far is there's 5 carbons and one of these carbons has an alcohol on it. It might be out here on the end. That alcohol or the alcohol could be on the 2nd position. So let's move the alcohol from the end to the 2nd position right here, or the alcohol could be in the middle of the compound. If the alcohol is out on the end, that means I have just a single methyl group. This is the only methyl group anywhere in the compound. Methyls are the only thing that should show up below 20 in your C-13 NMR spectrum. And you'll notice that I actually have 2 peaks below 20 in the NMR, in the C-13 NMR. That's a big deal. If something shows up below 20, it is almost always a methyl group, 98% of the time. And so the fact that I've got 2 of them would suggest that a compound that only has 1 methyl group is out. So this seems like the fact that this compound only has a single methyl group and my C-13 NMR is telling me I have 2. I'm going to go ahead and remove that compound from consideration. This compound right here has a plane of symmetry. These 3 carbons, the methyl groups are actually the same on the end. And these methylene carbons are the same, and that methine carbon is unique. So this would only produce 3 different peaks in my C-13 NMR spectrum. Since I saw 5 separate peaks in the C-13 NMR, that means that this compound is not correct. So this is my most likely candidate. I have the 2 methyl groups out here on the end. I have a methylene group right here, and I have a methine group right there. 5 different carbons, an alcohol, 2 methyl groups. Based on the evidence that I have, this is about as good as I'm going to get as an answer. So the answer is 2-pentanol. I'm going to let you go ahead and work on the remaining 2 and then upload your assignment. I've identified the molecular ion peak for you in problem number 2. Problem number 3, I did not tell you what the molecular ion peak is because there is kind of a special treat associated with you looking at that molecular ion peak and learning some things. But I did kind of already spoiler this one for you by pointing out the evidence for a benzene ring. So that's it. Good luck on this assignment, and I'll show you the answers when I post the next lesson video.